Let's get started. It is a pleasure to have Dr. Sudip Mukherjee visiting us here today. Sudip finished his PhD from SINP, where he submitted his thesis in 2019 and to CU, and there was a delay in getting the degree for about 1 year. And however, since 2015, Sudip has been teaching at this Barasat Government College, and his general area of expertise is non-equilibrium statement. And today he wants to talk about coupled exclusion processes. Please.
Thank you. Hello everyone. Today we are going to discuss our studies on non-equilibrium steady states in coupled asymmetric and symmetry exclusion principle. TASEV is a well-known model. It's a 1D open model which was originally introduced to describe the motion of messenger RNA along the ribosome in biological cells. Later we found it is also a very famous model which shows boundary-induced phase transition. Several variants of TASEV have been proposed and studied. We focused on the effect of linking TASEV with symmetry exclusion process or 1D diffusion. Before we go to our model, I briefly discuss the original TASEV model. This is the model diagram. This is the model diagram. This is a one-dimensional model where particle enter with the rate alpha and exit the system with the rate beta. Within the lattice, particle occupancy at inside is either 0 or 1. That is the exclusion. And particle can move only in one direction. That is the totally asymmetric. And these alpha beta are the tuning parameters or the control parameters of the system through which we can get many phases. Here is the equation of motion of the TASEV model. While Ni is the occupancy at any site I. Now using the mean field approximation, if we replace Ni by its average rho I, then the steady state equation of motion becomes this rho I minus 1 minus rho I minus rho I 1 minus rho I plus 1 equal to 0. Where I use the mean field approximation, these get all kind of fluctuations. And then considering continuum limit, we get this equation of motion 2 rho x minus 1 del del x or rho x equal to 0. Here x is a variable which is I by L. L is the system size. And this is the equation of motion in continuum limit. We can see in the equation of motion, the obtained solution of rho is x independent in bulk. We also identify the mean field current J as rho J equal to rho into 1 minus. Here is a phase diagram of the model. As I told earlier that alpha beta are the control parameter of the system. Then varying alpha and beta, we can get 3 phases. One is low density phase, which is LD phase, where alpha is less than beta. Go back to this. If alpha is less than beta means the exit rate is greater than the entry rate. So one can expect the particle density is low in the TASEV channel. So that is why it is called low density phase. Another phase is high density phase where beta is less than alpha and beta is also less than half. So you can also expect this because in this case beta is less than alpha, so the exit rate is less than the entry rate. So we expect high particle density in the passive channel. So this is called HD phase. And another the phase is MC phase, which is maximal current phase, where both alpha and beta greater than half, where the particle current is maximum. That is why it is called maximum current phase or MC phase. So it shows boundary-induced phase transition, which I talked earlier, that these models shows boundary-induced phase transition. Now I come to another model which discusses TASEV with Langmuir kinetics. It is a very interesting model where the TASEV is coupled to a particle reservoir and exchange particle with the rate omega A and omega D. But the omega and omega D are the attachment and detachment rates. If this attachment detachment rate, that means the on-off process, is competing with the TASEV hopping rate, then we get very interesting phase diagram. You see, in the earlier case, we have only 3 phases: pure LD phase, pure NT phase, and pure MC phase. Whereas when we coupled TASEV to a particle reservoir and the on-off process and the particle hopping is competing, we get not only the pure phases like LD, LDMC, we also get the mixed phases like LDMC, HDMC, LDSD, and LDMCSD. These are very totally new phase diagram we obtain when we couple the TASEV with a particle reservoir. Now I discuss a very well-known 1D equilibrium process, the simple exclusion process.
How do you characterize those phases? LD,
Oh.
LD,
One part of the TASEP is in the LD phase, another part is TASEP in the HD phase. So the one part of the density is below less than half, and the other part is greater than half. So there is a discontinuity at some point. This is actually called domain wall phase. Whereas in the LDMC phase, one part is in the below the half, and the other part in the on the half.
And in that case, what is the current?
Current is still rho into 1 minus rho.
No, that is correct, but current should be same everywhere. And we know that in the MC phase, current is maximum.
Yeah, but in this case, current is space varying, not constant. When we introduce the particle exchange in the system, the current is not constant, it's space varying. We get a space varying current in that case.
But when you write the so you cannot write the continuity equation.
Yes.
Right.
And does it depend on where exactly you are doing it, because it's an open model, right?
It's open.
So it should depend on like where you make the insertion or let us say using it at random. And how many size does should also
That debates between the MCS, not the image. There is another well-known equilibrium which is called simple exclusion process of state. In this case, unlike the TASEP, their particle can move in both directions. That is called simple exclusion, subject to the condition of exclusion. And within the bulk, the hopping rate is D, which is often called diffusivity. At the boundaries, particle can enter or exit within at half. The steady state is uniform and it is x-dependent. Its value is half. So in the steady state, the shape density is equal to half. This is a very famous equilibrium model. Now I come to our model. We actually couple this shape with the shape through particle exchange process. Our motivation of our study is to study the steady state produced by the interplay between the TASEP and the shape. You can see the model. The hopping rate in the TASEP channel is Q, and the hopping rate in the shape channel is now D, and the particle exchange rate between these two channels is omega. So these are the equation of motion of our model in the discrete limit, where Ni is the particle density at the ith side of the TASEP channel, and Nis is the particle density of the shape channel. Again, using the mean field approximation and considering steady state, we get this discrete equation of motion. If now consider the continuum limit, we get this equation of motion. One thing I should mention again, that when we discuss the LK TASEP, that means the TASEP with Langmuir kinetics, to get the reach phase diagram, we need to ensure that the TASEP hopping rate must be competing with the on-off states. So in our model, we also did this, that to make Langmuir kinetics competing with the other hopping rates, we scale omega as capital omega by L squared and Q as 1 upon L. And then considering thermodynamic limit, this equation of motion become omega c minus rho plus 2 rho minus 1 del x of rho equal to 0, and the del x square c plus omega rho minus c equal to 0. These are the equation of motion in the continuum limit.
What is C?
C is shape density. Rho is the TASEP density. Rho is the TASEP density. C is the shape density. Okay. Before I go to the detailed study of our model, I first discuss two. Okay, please.
Why do you scale those rates?
Particular fashion? Yeah. In this fashion, because to find the new phases, we have to make these omega exchange rates competing with these other rates, that is Q and with D. If we don't scale this, then one of those will actually supersede other. So that is why we need to scale this.
Okay, so why in a different fashion? I mean, you scale one with 1 over L, like one with L and one with L squared. So what is the motivation?
You just see this equation of motion. From here, you just see that is omega. If you don't scale this, E has a denominator 1 by L square. To make competing, you have to put either of if you multiply the L square, then omega L square should be should compete with D. That is with D. Omega into L square you replace by the capital omega. And if you see this, then if you see this, if you multiply it by the L, then omega L should compete with the Q. So that is why Q replaced by 1 upon L. You get it? So now we discuss the two extreme limit of our model. First, we consider D going to infinity. That means the diffusive dynamics is extremely fast, which essentially makes the other hopping rate, that means the Tassel hopping rate and the attachment detachment process, completely insignificant with respect to the diffusion. As a result, we can expect that shape is decoupled from the Tassel. So we get the shape density equal to half. And if we put this Cx equal to half in the equation of motion along with the d going to infinity limit, the equation of motion of the Tassel becomes omega equal to 1 minus 2rho plus 2rho minus 1 del x of rho equal to 0. This is the equation of motion of LK Tassel with attachment detachment rate omega by 2. So we can see if we take d going to infinity limit, our model reduces to the very well known model, which is LK Tassel model. Yeah. See that d going to infinity limit, our model reduced to this model, LK Tassel model. Now we consider other extreme where we consider d going to 0 limit. Then only the effective dynamics in the shape channel is the attachment detachment process. And the shape density effectively is slave to the Tassel density, which essentially mathematically gets Cx equal to rho x. And for with this Cx equal to rho x and d going to 0, the equation of motion becomes 2rho minus 1 del x of rho equal to 0. So if you go back to the slide of the original Tassel model, you see this is the actual equation of motion of the original Tassel model. So in the other limit where we consider d going to 0, our model reduces to original Tassel model.
What about the boundary drive? No, you still have the boundary drive, right?
Yeah, both are there. Alpha, but we just change the diffusivity. You take that two extreme limit,
Which
right?
of the symmetric process?
D is in a symmetry.
When D is 0, is
Yeah.
close to them, upper lane is frozen.
Huh.
But there is still particles being exchanged. So why don't you see LK?
Yeah. Why do this is because the particle you can think is like this. Suppose they are in the Tassel lane, the particle can effectively have two sides to hop. One is the original Tassel side, and another is the Tassel side on the shape. So basically, these attachment detachment have no effect on it. It's something equivalent to a Tassel having two sides and double size Tassel, something like this.
Attachment detachment is still happening. That rate you have not taken.
Yeah.
Let's say this lateral diffusion is stopped.
Yeah.
So therefore now I have a totally asymmetric exclusion. Attachment and detachment. Maybe it is not a. I mean, this lane is frozen, so it is some. It may depend on the initial condition, but it is still. Why don't I see the effect of omega? That is what I don't understand.
So you do see, because omega is there, rho equal to c. Because if you see it from the same point of view, there is only one side, and it exchanges with another side. The only solution is rho equal to c when two exchange processes are equal. That's the only solution.
Oh, sorry, in the same.
Yeah, we get the only solution C equal to rho in that case. If we go to
What
the
is C?
shape density. Yeah, if you put D equal to 0, the only solution is rho equal to C. So we have the effect through this
And rho is
Tassel density. Tassel density.
So maybe this is the steady state condition, right? So if
Yeah.
rho equal to c, then the steady state will be reached.
These are only solution is rho equal to C. If you put D equal to 0 there, the only solution is rho equal to C.
Otherwise, the system won't reach steady state.
Yeah. Right. So you see in the two different limit, two extreme limit, our model reduced to LK Tassel, and that for the D is equal to 0 limit, our model reduced to pure Tassel model. Now we're interested in for the intermediate values of D. We examine the crossover from the Tassel dynamics to the LK Tassel dynamics by varying the strength of the D. Before we go to the further details, we mentioned that from the equation of motion of Tassel one shape, we have a conserved quantity J, but J equal to 2x minus 1 whole square plus 4d del x of C. J is not a physical current. It is actually related to the physical current via this relation J equal to 1 minus 4 J dot. But J dot is the total current through the shape and Tassel channel. Now we construct the mean field theory for the large G. Okay.
Total current is the shape how, I mean, through attachment detachment.
No. This is the lateral
In safe, the protocol is 0, right?
When it's isolated.
Yeah, so
But
is
when-
0, and
yeah,
from to attachment, it is
Yeah,
0.
First, we discuss the mean field theory for the large D limit. If we consider the D is large, then we expect the Tassel density will be very close to the density for the LK Tassel model. Similarly,
So I don't think it will be only coming back to Thomas' question. I don't think it is only one model. I don't think it is only because of the evaporation deposition process that gives rise to current. Because the Tassel channel is a density gradient.
Yeah.
Which would mean that in some part desorption is more likely, although I am choosing it at random.
Yeah.
In some part desorption is more likely, in some part adsorption is more
More
likely. So this may give rise to a density gradient in the same channel, and there may be diffusion induced current.
Even
Do you not see that? Can you rule it out? Maybe I'm missing something.
in a particle current, we not explain from the MFT, calculate from the MCS, we get very low particle current.
No, but if you measure the density profile,
Yeah.
do you see a gradient?
Yeah.
That will
I'll
be-
come to this. I'll
Then
come to
there
this.
is, this is not the only current. There is current induced by diffusion.
Huh. No, he's asking the safe current will be 0. I am saying that it will be 0 when it's completely decoupled from the Tassel. So isolated safe, the current should be 0. That is a safe. When it is coupled to it, there has to be current due to the attachment process and also for the lateral movement in that. MFT for the last D, what I said that if we consider D is large, and we also know that in the D going to infinity limit, our model reduces to LK Tassel model. So one would expect for the large D, the density is very close to the density profile for the LK Tassel model. And also in the large D go to infinity limit, we have the safe density C equal to half. So we can expect for the large D, that C density C should be very close to half. So we can propose this form of density. Rho x equal to rho L kx plus del rho and Cx equal to half plus del C. But del rho and del C are the modifications to their asymptotic results. Of course, del rho and del C are very small. Now, if we substitute these rho and C in the equation of motion, where rho Lk actually satisfies this equation of motion, 2 rho Lk minus 1 del Lx of rho Lk minus omega 2 equal to 0, and from which we get two solutions of the rho Lk. One is rho Lk equal to half, which is uniform solution, and another is rho Lk equal to omega 2x plus rho 0. And these rho 0 dependent upon the nature of the phase of the Tassel. I'll come to this later. So if we substitute this rho x and Cx on the equation of motion of safe and Tassel, we get the solution for the del C and del rho. You see, in the expression of del C, there is rho 0. As I mentioned, the rho 0 depends upon the phase of the Tassel. So you can say that del C and hence also the C depend explicitly on the boundary condition of the Tassel density through this parameter rho 0.
Is the first order change or what?
Huh?
Is it first order?
Yeah, we continue only linear on delta C and delta rho. And this is the solution of the del rho, where the K is the integration constant. These are the values of the other constant. In the LD phase, rho is equal to alpha, and then accounting the boundary condition, del rho should vanish at the boundary x equal to 0. We can evaluate the K0, and hence we find the density profile in the LD phase, which is rho LD. The expression of rho LD is this. And the corresponding safe density will be C, this is C minus x. Again, considering the value of the rho in the LD phase, which is 1 minus beta minus omega 2, and considering the boundary constant del rho should vanish at x equal to 1. Sorry. So this rho SD and the C class is the rho SD is the density for the HD phase of the Tassel, and the corresponding safe density is C plus. To verify our accuracy of our MFT predictions, we perform on-the-color simulation. Here the blue lines are the lines coming from the MFT and the red dots coming from the MCS simulation. We perform the MCS study with systems as L equal to 1000, D equal to 1, and omega equal to 0.3. You see excellent agreement between the Monte Carlo result and the MFT results. Here is the phase diagram of the model. This is the phase diagram of the TASEP. We can see we have the pure phase, also the mixed phases. And to find the phase diagram of the shape, we define a quantity C bar, which is actually the average density of the shape channel. When C bar is greater than half, we set the phase in the excess phase. When C bar is less than half, we set the shape in the deficit phase. Whereas when C bar equal to half, we set the phase in the neutral phase. So here is the phase diagram of the shape channel. We should mention that there is a correspondence between the passive phase diagram and the shape phase diagram. For example, with a system in the LD phase or in the LDMC phase, the corresponding phase in the shape channel will be deficit. Now we discuss the AFT for the small t. As we already know that we have a conserved quantity J equal to 2x minus 1 whole square plus 4 del x of C. You can see this is a quadratic equation of rho. So from this we can have two solutions of rho, which is rho plus minus. Rho plus is actually greater than half and rho minus is actually less than half. As we consider in this case d small, so we can approximate the solution of rho plus minus s like this. And if you now substitute this in the equation of motion of C, we get a closed equation of for the C, which is d del x of C, a plus minus del x C plus omega Cx minus b plus minus equal to 0. So this is a closed equation of C, from which we can evaluate the C. But J plus minus have the values of A plus minus equal to plus minus omega by dj plus minus, and b plus minus equal to half 1 plus root over of j plus minus. And the value of the j plus minus are given by like this: 2 alpha minus 1 whole square and j plus equal to 2 beta minus 1 whole square. So from this differential equation, we have two solutions of C, there is C plus and C minus, where U1 plus minus and U2 plus minus can be evaluated using the boundary condition. C0 and C1 both should be half. Then we evaluate the U1, U2, and we get the expression of the C plus minus. Now using the C plus minus, we can find the solution of the rho LD and rho HD. You can see rho LD equal to half 1 minus root over of JLD 4D del x of C minus. This is quite evident, this is less than half, and rho HD is equal to half into 1 plus root over of JHD 4D del x of C plus. It is greater than half. So these are the solutions for the LD phase and the HD phase. Again, to check the accuracy of our MFT, we perform Monte Carlo simulation with the same system as L equal to 1000. Here we consider D equal to 0.01 and omega equal to again 0.3. We see that the good agreement between the inactive result and the MCS. Now is the time for SASE phase diagram of the model, and that D is very small. We should mention that the shape phase diagram should remain same for any finite value of D. This is come from the particle hole symmetry. If we consider the particle hole symmetry, then the total area of the LD phase region, which includes both pure LD phase and the mixed phases, that is the LDMC phases, this should be equal to the total area of the HD phases, which includes HD and the HD parts of the mixed phases. And these two areas has to be placed symmetrically about the line alpha equal to beta. So as we already mentioned, there is a correspondence between the passive phase diagram and the shape phase diagram. You can expect, due to this symmetry and the correspondence between the passive and the passive phase diagram and the shape phase diagram, the shape phase diagram remains same for any finite value of D. We mentioned that if we reduce the value of D, we get a crossover from the LK dynamics to passive dynamics. This thing can be examined to inspecting the change in the nature of the phase diagram with the variation of D. You see, here I plot phase diagram for several values of D. And if you see in the LK TASEP, we have mixed phases, whereas in the pure TASEP case, we have only the pure phases. So if you just plot the phase diagram by decreasing the value of D, at one stage, if you see this value D, you see there is no mixed phases, there are only pure phases. So you can see the model reduced to make a crossover from the LK TASEP to TASEP dynamics from the inspection of the phase diagram. Lastly, we study the delocalization of domain 1. We know for the LK TASEP, the domain 1 is localized, whereas for the pure TASEP system, domain 1 is completely delocalized. So if we reduce the value of D, then one would expect there is a gradual delocalization of domain 1. To see this, we compute domain 1 densities for these values of D and measure a quantity W, which is roughly the projection of the domain 1 density on the x-axis. You can see if we reduce the value of D, we get an increase in the value of omega W, which clearly indicate the gradual delocalization of the of domain 1 with the decrease in the value of D.
So we need to get
That is why you need to plot in a log scale.
that's why it's said.
So again, to compute the domain 1 density, we consider alpha equal to beta equal to 0.1 and omega equal to 0.3. Again, the system size is L equal to 1000. So here's the summary of our work. We know we have a famous non-equilibrium model TASER. On the other hand, we have another famous equilibrium model SAFE. We couple these two things, the model to particle exchange. And we find in the two extreme limit for the diverging and the vanishing, our model reduces to LK TASER and TASER respectively. Surprisingly, SAFE parameter D, which is diffusivity, appears a tuning parameter for the TASER. And we also find and due to the mutual coupling of the SAFE and TASER density, we get non-trivial space dependence of the density profiles. And lastly, we see that with the gradual reduction of the D, we get gradual change, with gradual delocalization of the domain. So here I acknowledge the ACRB DST for financial support of our work through CRG scheme. And this is a reference of our paper, which is present accepted in the PRE and presently in production. Thank you.
Questions? Yes, sir.
There any biological system where particular this type of model where they're neighboring lane and particle exchange is happening from one lane to other and one is safe and one is passive?
Not exactly, but there is some biological instances there. The cytoskeleton motor, when sometimes detached from that path channel and diffused into the cytoplasm, and then again come back to the channel. So this is exactly equivalent to one.
So one thing that was mentioned, like extreme case when D is 0,
Yeah.
as Ram was mentioning, that there should be still a signature of this LK.
Yeah.
But I think, is it the same case? Like you scale the exchange rates, the omega is the exchange rate, you scale it with L square, and if you tend it to infinity, then the information gets washed away and you get only passive kind of thing. It is because of the scaling.
No, there is not a because of scaling, because if you don't perform any scaling, you just see if there is no diffusion in the channel, the only particular determinant is there.
Okay.
So
and you don't scale it with anything. So you will not get LK passive, you will get the passive.
Yeah. But your question is, why am I getting the TASEP density profile for D going to live? Is it due to the scaling or not?
Yes, exactly.
Okay.
Yes.
Yeah. But from this, you are saying if we don't take these limits, even if we don't scale it, if you see this equation of motion, if we put D equal to 0, the only solution is rho equal to C, which again reduces the solution 2 rho minus equation of motion 2 rho minus 1 del x equal to 0. So it is not due to the scaling. Even if you don't scale it, from this bare equation of motion, you can find this the model reduced to the TASEP model when you take D going to 0 limit.
Yes, I understand. I mean, your motivation for the scaling was to
make competing. Yeah.
So when D is already 0, so everything is
had. But we are not doing with only the extreme case. We need to perform the similar case for the intermediate value of the D.
Okay.
For the extreme, we do not need to scale this because we don't have the D, and we have simply equation of motion of rho. So we have to deal with the intermediate values of D. That is why I need to scale it to make competing the hopping rates with the particle attachment rates. Okay.
Any other questions?
And beta coming from the particle reservoir. Entry rate and
Yeah.
how is it different from the detachment and attachment of the particle?
Now, alpha beta introduced the particle from the laterally, but the attachment deterrent process actually make the particle exchange between these two channels. These are, suppose you can think is like that. Here is a the particle is about infinite capacity, here the particle is infinite capacity. And from here, the particle enters the system with alpha and leaves the system with beta.
You are asking in an actual physical system, experimental. So the question is, in an actual physical system, can you tell the difference between alpha, beta, and omega?
Huh?
Because both are introducing part. For example, if I take the last side, so
Yeah.
I see some particle there. Did it come from absorption, desorption, or from entry? Can you distinguish the two processes?
That we are saying, suppose we have a particle there. So it can leave the system with a beta, or it also can come.
In a physical system, is it
Yeah.
possible to distinguish between these two rates? That was the question.
What is saying that these two is actually completely different, because at the boundaries, not in the bulk, there is no alpha beta is there, but in the boundaries, you have the alpha beta as well as the omega. One thing is there, because for the if you consider the omega, then there is a subject of sorry. There, just a minute. If we consider the omega, there is a subject of exclusion. But in case of only beta, there is no subject exclusion. The particle can simply leave the system. But if the system, if the particle want to come from here to here, this side.
That is part of your model.
Yeah.
The question was, can you?
Reality.
Any other questions?
There is any kind of ordering omega, that means the attachment detachment rate.
Yeah.
Like, can expect the same kind of case here.
Actually, we do not consider beta in the omega. That is, you are saying omega is space dependent. Then see, we actually tried this. We get some effective result, which is very complicated. From here, we cannot infer the steady state nature of the series. But one thing we can sure that we'll get some space dependent rho and c, but the exact quantitative nature is not known.
Is dependent omega is just omega 1, omega 2.
Omega 1, omega 2 means that means what the omega 1 attachment and omega detachment, something like this.
Upper limit to lower than omega 1, lower
Okay.
limit to omega, upper limit to omega 2, and they are different. Then this situation is
We need then we will need through this. But with the in case LKT says the original LKT says we actually get this phase that are constant both omega and omega d equal. We haven't studied this. These are very interesting questions we need to address later.
And how does the diffusive time scale? You can only assign time scale with diffusion, right?
Yeah.
And omega. So we can look at comparison between these two time scales.
Yeah, we make computing with the, and through this scale. Omega equal to capital omega by L square and Q equal to 1 by L. These things make this two hopping there's complete.
What can you say about the dynamics of the system? You have presented results for the phase diagram.
Yeah.
But can you say anything about dynamics?
Dynamics that what do you mean? That means
Correlations.
correlations in the extended you see that when d going to 0, the road is safe density is completely safe to the road passive density. And
No, the dynamics, the dynamical properties.
Like rho xt, rho x0 correlations. Like spine.
oh, that we don't study it. We cannot say right now. Sorry. When you are saying that the some correlation rho xt, rho x0 something that we don't study.
Any other questions? If not, let's thank Sudip once more.
And,
And if you yes,
yeah.
we touch the mic.